Hello, everyone. My name is Will. I'm very excited to be here today during virtual WINE 2020, and I would like to thank the organizers for all their efforts into running this conference virtually. And I'm an assistant professor in Columbia University in the DRO division of the Graduate School of Business. So today I'm excited to talk to you about revenue optimal deterministic auctions for multiple buyers with ordinal preferences over fixed price items. Okay, so I'm going to explain what this is, and the way I'm going to explain how we arrived at this problem is actually by starting with the assortment optimization problem, which is a very well-studied and practical problem in retail. So what is assortment optimization? It's imagine you're running a massage salon where you have three different options. You could either give a full body massage for $600, or a back rub for $400, or a foot rub for $300. And an important assumption in the assortment optimization problem is that the prices here are fixed, which means that these are market established prices that you do not have control over. So I can't change the prices of my services. But what I do get to control is the subset of services that I actually show to the different customers on my brochure. So, and the ranking preferences part means that each customer has some ordering of preference over the different massages they could get. So their unit demand, each customer wants at most one. But for example, my first customer, their first choice might be the back rub, and their second choice might be the full body massage. So if I offer every massage option, then the first customer will choose the back rub. Maybe the second customer is an athlete and they only want the foot rub, so they'll choose the foot rub. Maybe the final customer is a student, so they're similar to the first customer, but they're more price sensitive. They can't afford the full body massage, so they only want a back rub. So this is what would have happened if I showed all the options. But maybe I could increase revenue by, for example, not showing the back rub, because then from the first customer type, I'm going to get them to, they're going to then get their second choice of the full body massage, and I'm going to get $600 from each of the business customers of the first type. But then for the students, they're not going to get any massage and they're going to walk away purchasing nothing. So whether it's increases revenue to show versus hide the back rub depends on the propensity of business customers versus students in my pool. So this is an optimization problem over subsets. It's NP-hard in general. And the key challenge here is cannibalization, where adding certain products into my assortment that I show will cannibalize the sales of others because the customers are unit demand. Okay, and then over time, assortment optimization has gotten more sophisticated. If you imagine an online platform like Amazon.com, they don't have to show everyone the same assortment. So maybe based on an IP address, I know that this IP address has a greater propensity of business customers. So maybe I'll hide the back rub from them, and then I can make more money. And yeah, so you can show different assortments. You can think of this as like different personalized recommendations that Amazon.com makes, or I guess in China it would be Alibaba, I think. And yeah, so you can show these different assortments and potentially increase your revenue. Another way in which you can think about the personalized assortment offering is just like ranking the search results differently. And this is true on Amazon. If I make a search on Amazon for shampoo and you do as well, we could see a different ordering of results. Okay, and so the personalized assortment optimization problem in theory is just repeated instantiations of the assortment optimization problem, But what ties it together is the fact that there's a capacity constraint. So maybe I have a limited number of massage slots throughout the day. And maybe I only started with 2. And then after selling a massage to the first 2 customers, I have no slots remaining. And then my final customer, who's a student, I have to turn them away. So in the personalized assortment optimization problem, it sort of builds an optimal stopping problem on top of the assortment optimization problem. And yeah, the challenge is this online allocation of limited massage capacities. Okay, so the motivation for this work is, of course, the challenge of online customers arriving is that I have to make my allocations in an online fashion. But can we run an auction in the assortment setting to have higher revenue allocation? So for example, maybe my 3 customers arrive at the same time. They each report their preference ranking, and then through some kind of mechanism, I decide which massage to allocate to which person, subject to the constraint that I only have, in this example, 2 massage slots. And yeah, so the challenge here is getting the customers to truthfully elicit their rankings, as is the standard challenge in the optimization problem of mechanism design. So now let me formally state our problem setup. So I have n products with fixed exogenously determined prices, R1 through Rn. I have m buyers. I'm going to let bolded L denote the profile of lists. So each L is an ordered subset of the products that the buyer is willing to purchase. A mechanism in this setting is going to be a mapping from a reported profile of lists to an allocation for each buyer, which is going to be an index either 0, 1, ... n. So basically, let's say if ji of L equals 5, that means buyer I gets to purchase product 5 at price R5. And if ji equals 0, that means the buyer purchases nothing. Okay, so I'm going to assume that the mechanism has to be deterministic because I'm not going to define how the buyer chooses over an uncertain outcome when they only have an ordinal ranking. And consequently, I'm going to assume that the mechanism has to be dominant strategy truthful. And so I'll clarify what these mean on the next slide. So this problem, like usually in assortment optimization, takes place in a Bayesian setting where each L is drawn independently from a known distribution Pi. The buyers could have different list distributions. And the objective of the mechanism designer is to maximize the expected revenue. So formally, this is how you would write the optimization problem. So as you can see, the objective is I'm taking the expectation over the list profile L, which is drawn from a product distribution, and then I'm summing the fixed prices RJI of the products that are allocated. So now, just to clarify what the incentive compatibility and individual rationality constraints are. So I'm going to let L minus I denote the reports of the buyers other than I, which is standard notation. So incentive compatibility basically says that if my true preference is Li, then whatever item I get by truthfully reporting Li, I'm going to prefer that over whatever item I would have gotten by telling some lie L prime of I. And similarly, for individual rationality, it says that whatever item I get through truthfully reporting Li, I'm going to prefer this over this no purchase option. So in other words, the mechanism can't force any buyer into purchasing a product that they rank below the no purchase option. And this has to hold true under all possibilities for L minus I of what the buyers do. This is the stronger dominant strategy truthfulness. Okay, so I just want to say our problem is a generalization of the assortment optimization problem. So this is actually important. It's easy to see, but let me explain this. So in assortment optimization, the decision, instead of specifying a mechanism, is instead to specify a subset of products that you're going to show the customer. But it's actually easy to see that with one buyer, the incentive compatibility constraint basically says there's going to be some universe of possible products the customer could get if you take a union over all the lies L prime they could tell. And then that assortment, that set of products that you get by taking this union is equivalent to the assortment that you're showing the buyer. So it's actually not hard to see that this is an equivalent formulation of the assortment optimization problem where you need to decide on a subset to show if there's only one buyer. And so assortment optimization for general list distributions has actually been shown to be MP hard. It's actually as hard as max independent set. So we're not going to hope to be able to polynomially solve this problem in general, but for specific list distributions, that's where our results are going to lie. And then also I want to say our problem is a relaxation of the personalized assortment problem. Where here is like in the motivation, here essentially all of the customers are arriving at the same time instead of sequentially. So we can have a higher revenue mechanism than an online assortment mechanism. Okay, so one assumption I make throughout this work is, like in the massage example, I'm assuming that the capacity constraints only depend on the set of buyers served. So by this, I mean the buyer is a winner, or they get served if and only if ji is not equal to 0. So basically, this means buyer I gets some type of massage. And I'm assuming that my capacity constraints are only on how many buyers I can give a massage to. Or more generally, a downward closed constraint, script F, that the set of winners must lie in. So this concept has been previously introduced in Alai et al. 1213, where they study service-constrained environments. And so I'm going to assume that we have service-constrained environments. So having gotten that out of the way, I'm going to introduce the last constraint in our optimization, which is that as I explained, the set of I, that ji of L doesn't equal 0, so this is the set of winners, it has to lie in script F. And yeah, so this is also in revenue management. It corresponds to the single leg revenue management problem. And actually for this talk, I'm going to focus on the further simplified case where the capacity constraint is just there can only be one winner regardless of which product they get. But our results hold for general service-constrained environments. Okay, a quick comparison of our problem to related literature. So I would say it draws elements from 3 different strands of results. So the first is allocation mechanisms without money has obviously been well studied. Our problem is most related to the house allocation problem and these one-sided matching markets. The main difference is that we're doing revenue maximization in a Bayesian setting, whereas a lot of these papers focus on singularity results that say, like, under certain conditions, there exists a unique mechanism, results of that form. Secondly, our paper is related to assortment optimization and the more general personalized assortment optimization. So this is something that's studied a lot in my field. And the difference is we're the first to view these assortment optimization problems from a mechanism design lens. And finally, Bayesian revenue maximization is well studied, even in the case of unit demand buyers. And the main difference between our work is that we're assuming the payments are fixed. So we're restricting to these ordinal preferences and these mechanisms that don't charge arbitrary prices, whereas the works listed here, they allow for arbitrary payments and randomized mechanisms. Okay, so let me now introduce our main results. So first, I want to point out that a starting point for assortment auctions. So that's what I'm going to call the problem I'm studying. Is that in the special case where customers always prefer lower priced products over higher priced products. So in this example with the 3 types of massage, it would mean that suppose the only possible rankings were customers prefer lower priced products over higher priced products up to some maximum willingness to pay. In this case, basically, each of the possible rankings is equivalent to a valuation. And a distribution over lists that are restricted to this support is actually equivalent to a valuation distribution. And then under the service-constrained environment assumption, our problem actually, it's not hard to see, it's equivalent to just a classical Meyerson's revenue maximization problem. So the solution was already given by Meyerson in 1981, which says for each buyer, you give them an ironed virtual valuation based on only their reported valuation and valuation distribution. And then the revenue maximizing mechanism is to give the item to the buyer who has the highest non-negative virtual valuation. Okay, so the key structure in Meyerson's optimal auction is that a buyer's priority for winning the auction is captured by a univariate virtual valuation, which you compute only based on what they report and what their prior distribution is. It doesn't depend on how many buyers there are, what the other buyers' reports or distributions are. So our first result is that we show that if you try to take such an approach for general preference distributions, it actually doesn't work. So we can provide an example that shows even when there's 2 IID buyers, if we allow for arbitrary preference distributions over lists, then we can construct a case where in the optimal auction, you want something like buyer 1 wins when they report the same list, and buyer 2 wins when they report different lists. So an optimal mechanism of this type cannot be captured using virtual evaluations. So even structurally, when we generalize from the valuation distributions to list distributions, structurally, even under a single winner auction, the optimal mechanism might not be captured by virtual evaluations. Okay, so our main positive result is that for a specific class of preference distributions, namely Markov chain ranking distributions, that the optimal assortment auction actually does follow virtual evaluations. So let me explain this. So far I've told you for buy down preferences, Meyerson is optimal. Generally speaking, virtual evaluations are not optimal. And yeah, so our main positive result is that for this rather large class of choice models, the optimal auction can be implemented by virtual evaluations. So it actually captures, I would say, a lot of the choice models that are commonly studied. So specifically, it captures multinomial logic, which is the most commonly studied choice model used in practice. And it also captures the case of independent demand, also known as single-minded buyers. So that's a simple case where each buyer only wants a single item. So our main result actually generalizes Meyerson's result, at least in the case of discrete valuations, and then also extends it to the case of multinomial logic choice models. Okay, so let me now explain what a Markov chain choice model is. And this is a studied class of choice models, and you can also perform estimation on this class, use it to model consumer choices based on real data, as shown by the pioneering work by Blanchet et al. In 2016. So in a Markov chain choice model, basically I have a Markov chain over the set of products and the no purchase option 0, where each product appears exactly once. And then I have these starting probabilities, lambda. So what the lambda j's tell me is the probability that the list starts on node J. So in this example, the list starts on the back rub with probability 2/3, and the list starts on the foot rub with probability 1/3. So there's these transition probabilities between nodes. We transition along the Markov chain. And the rule is whenever we visit a node for the first time, we add it to the list. And the list stops. So in other words, that's the end of the list of products the customer is willing to purchase as soon as the node 0 is hit. And it's assumed that this happens with probability 1 in the Markov chain. So this Markov chain here corresponds to the following distribution over lists. A third of the time, I go like this, and my list is back rub, full body. A third of the time, my list is just a foot rub. A third of the time, my list is just a back rub. Okay, so our primary positive result says that for Markov chain choice models, the optimal auction can be polynomially computed, and it's structured in the same way as Meyerson's original auction, which is each buyer reports a list, and then they're assigned a virtual valuation, which maps the list to a single real number based on what they report and what their distribution was. The winner is then the buyer with the highest non-negative virtual valuation, and the winner chooses their favorite product from an assortment, which is decreasing basically in how much competition there is in the auction, which is the same way Meyerson works. And then in expectation, what you collect from this winner is equal to the expected virtual surplus as defined through these virtual valuation functions. So in the special case of one buyer, we can show that our optimal auction actually just corresponds to offering the revenue maximizing assortment to that buyer. And actually our work implies a new way of computing this optimal assortment. So it's already been known that assortment optimization for Markov chain choice models is polytime, but we actually, the special case of our result for one buyer actually derives a new way of generating an optimal assortment. And then on the other hand, in the special case of buy down preferences, our result reduces to Meyerson's main result, as I've already explained. So our notion of generalized virtual valuations for list distributions captures both of these results. And let me quickly show you how we get our Markov chain of virtual valuations. So basically, we construct them based on the revenue curve, which means we plot on the x-axis the sales probability of each of the possible subsets you could offer. On the y-axis, we plot its expected revenue, like so. And then we take the upper concave envelope of this. This is called the revenue curve. And then basically, the virtual valuation of a list, what we do is we look at the slope of the revenue curve. So initially, the slope in this example was 600, and the item on the assortment corresponding to this is A. So we're going to define the virtual valuation of any list that's willing to purchase the most expensive product A to be 600. And then we continue. So if someone is not willing to purchase A, but willing to purchase C, then their virtual valuation is 300. So that's a slope of this, and etc. So I just want to illustrate some intuition for the virtual valuations on this specific example. So there's a peculiarity here where if I look at the list consisting of the foot rub, the second item, the virtual valuation is 300, where the price of the foot rub is 300. Whereas for the back rub, even though the price was 400, the virtual valuation is only 200. So why do we get this non-monotonicity, it seems like? And the main reason is because the back rub cannibalizes the sales of the most expensive full body massage, which we're trying to sell as much as possible for $600. So in other words, we have to give the back rub a lower virtual valuation to punish the fact that it cannibalizes the full body massage. So we have this non-monotonicity here, but as long as the list distributions come from a Markov chain choice model, we can still get incentive compatibility and derive the optimal auction this way. Okay, so I'm going to skip the key steps in the proof of optimality. And finally, let me quickly comment on how our problem relates to personalized assortment optimization. So I said at the beginning, our problem is a relaxation of the personalized assortment problem. So actually, it can be seen that this is equivalent to the profit, the role of the profit in an online selection or an online pricing problem. So our work actually shows how to convert any profit inequality into an algorithm and a guarantee for personalized assortment under Markov chain choice models and service-constrained environments. But I should say, actually, even without these assumptions, even if you forget both the Markov chain assumption and the service-constrained assumption, this concept of assortment auction that we introduce still is a tighter relaxation of the personalized assortment problem that's sort of equivalent to the profit relaxation in online selection and pricing problems. And I'm excited about this in the future because it allows us to essentially derive stronger guarantees for personalized assortment. Because previously in personalized assortment, you always used the looser, what's called the ex-ante relaxation, and you were kind of like stuck there. You couldn't do better because there wasn't like a tighter relaxation to do your analysis relative to. But here, even without these assumptions, just the concept of an assortment auction could prove to be useful. Okay, and then I also want to mention in some ongoing work, I'm also studying randomized mechanisms for ordinal preferences over fixed price items. So here, even with a single buyer, the problem becomes interesting because you're optimizing over a larger class than just assortments. Okay, so in the interest of time, I'll stop there, and I thank you again for your attention.